In this presentation, we have to talk about Green's theorem in the plane. For that, consider an xy plane. R is the region surrounded by a curve. If you draw a line parallel to the x-axis, that should meet the curve at 2 points. In the same manner, if you draw a line parallel to the y-axis, that should meet the curve at 2 points. If m of x comma y and n of x comma y be the continuous functions of x and y having continuous partial derivatives dou m by dou y and dou n by dou x in a region R of the xy plane bounded by a closed curve C, then integral m into dx plus n into dy is equal to double integral of dou n by dou x minus dou m by dou y into dx dy. This is our Green's theorem. We have to prove this. Suppose the region R is bounded between the lines x equal to a and x equal to b, and two arcs a, e, b and b, f, a. Then the equations corresponding to the two arcs are y equal to f1 of x and y equal to f2 of x respectively. Furthermore, the value of f2 of x is greater than f1 of x. This is the curve. The lines x equal to a and x equal to b are providing the lower and upper limits of x. Then the equation y equal to f1 of x and f2 of x are giving the lower and upper values of y. Now we have to find out the integral value. First we should find out double integral of dou m by dou y into dx dy. This is equal to integral limit varying from a to b, then y equal to f1 of x to f2 of x. The lower limit of y is f1 of x, upper limit of y is f2 of x. Here the lower limit of x is a, upper limit of x is b. Then write down the function dou m by dou y dx dy. Now we should make our integration with respect to dy. The entire should be multiplied by dx. Then this is equal to integral limit varying from a to b. Then if you integrate this function dou m by dou y dy, then we can get m of x comma y. Then the lower limit of y is f1, upper limit of y is f2. Entire is multiplied by dx. This is equal to integral a to b m x comma upper limit is f2, upper value of y is f2 minus m of x comma lower limit f1, entire is multiplied by dx. Now we have to separate this into two integrals. This is equal to integral a to b m into x comma f2 into dx minus integral limit varying from a to b m into x comma f1 into dx. Then this is modified as minus of integral limit varying from b to a. This a to b is changed as b to a with a negative sign. M into x comma f2 into dx minus a to b m into x comma f1 into dx. The left hand side is dou m by dou y into dx dy. Then this is modified as, take the minus sign as a common term, integral, write down this term first. We have taken out negative sign outside, so a to b m into x comma f1 into dx. Already we have taken out this negative sign outside, so plus b to a, integral limit varying from b to a, m into x comma f2 into dx. Then this is minus of, this is our integral m into dx c, closed integral. This is m into dx integral. This negative sign is maintained as such. Integral m into dx equal to integral limit varying from a to b m into x comma f dx plus integral limit varying from b to a m x comma f2 into dx. The left hand side is double integral of dou m by dou y dx dy. From the above relation we can write integral m dx limit is closed curve. Integral m dx equal to minus of double integral of dou m by dou y into dx dy. Keep this as equation 1. Just I have multiplied both sides by a negative sign. Minus of dou m by dou y dx dy equal to integral m into dx. In the same way, we can prove integral n into dy, which is equal to double integral of dou n by dou x into dx dy. This is equation 2. Now add these two cases. From adding equations 1 and 2, we get left hand side is m into dx plus n into dy. Just we have written this as a single integral. Integral m into dx plus integral n into dy. Integral of m dx plus n dy, which is equal to double integral of, write down this term, positive this term first, dou n by dou x minus of this term, dou m by dou y. The entire is multiplied by dx dy. Just we have to add these two terms. Dou n by dou x dx dy minus dou m by dou y dx dy. We have taken out dx dy as a common term. This is R. Hence the theorem is proved. Now we have proved that m into dx plus n into dy equal to dou n by dou x minus dou m by dou y into dx dy. This is called the Green's theorem in the plane.